Good morning, good afternoon, or good evening, depending on where you are. I'm Zdeněk Přikril, CTO at Codasip, and today I'd like to talk about the application class of RISC-V processors that we have. And I'd like to share a few announcements with you today as well. The agenda of this talk is as follows. So firstly, I'm going to introduce the company, who we are, what we do. Then I will dive into the class of application processors that we have in more details. More particularly, I like to spend some time on the P extension that's part of the application class processor, as well as on the multi-core solution, or multiprocessor solution, if you will. So who is Codasip? Well, Codasip is leading provider of RISC-V processors IPs, as well as design automation tools for the modification of these IPs or customization of these IPs. Codasip was founded in 2014 in Brno in the Czech Republic. We are founding members of RISC-V Foundation, and we are active members of several task groups and open source projects that are related to the RISC-V, such as OpenOCD or LLVM. We introduced the first RISC-V IP back in 2015, and since that, the family of RISC-V processors become more rich. The headquarters is based in Germany. The R&D centers are in Europe, namely in the Czech Republic and France. The R&D consists of veterans or experts in the CPU designs, as well as on the cache coherent design and verification. We do have offices also around the globe, such as in China, such as in Shanghai, or US. Now, if you look at the solutions that the Codasip provide, there is a Codasip RISC-V processors, that the family portfolio that I was talking about. But we do have also the Codasip Studio, that's the EDA tool by which you can customize the IPs if you need it. Last but not least is a Codasip Swerve core support package. That's an environment for deploying of the Western Digital's open source cores, namely EH1, EH2, or EL2. So everything you need for deploying of this core, you can find it in the Swerve core support package, because we have tightly coupled with the Western Digital. In this presentation, I will focus on the first two items, so mainly on the RISC-V processors and the Studio. So let me introduce the RISC-V processors in a more general way. As you can see in this table, this is quite a big one. So you can see that at the columns we have classes such as low power, high performance, or application, and then in the rows you can see series. Depending on the application needs that you have, you can pick and choose whatever is in this matrix. So, for instance, if you're looking for the low power core that needs to run either bare metal or FreeRTOS, then you can go with the 1 series or 3 series, or eventually 5 series as well. You can enable certain features such as the floating point unit or caches in this class as well. The series basically determines the basic feature set, such as number of pipeline stages or the ISA or number of registers, and then you can combine that with the additional features such as the caches and so on. But in this case, in this presentation, let's look at the application class. In the case of the application class, we can see that we have 4 items there. So it's A70X and A70XP, and then we have the -MP suffix. So these are the cores. If you are looking for rich OS support, such as Linux, it means that you have enough power in this cores, as well as enough feature set to run this rich operating system. And I will dive into more details later on in this presentation. Before that, the common features that each of the member of the family has is that, they are available immediately. All of them are RISC-V compliant, and it's not only on the ISA level, but also on the privilege spec level or the debug spec level. All of them are pre-verified because we are huge believers in verification, so we are spending a lot of time for the verification process. All of them has industry standard interfaces, which means that for the debugging we are using SJTAG or CJTAG. In the case of the memory subsystem, we are using the YAMBA interface, which is either HB, EXI. All of them are customizable and configurable. Now, in the case of the RISC-V world, the configurable means that you can pick and choose from the options that we already verified. They're already for you. The customization means that you can add missing pieces there. So you can add a new instruction set, or you can change the microarchitecture if you need that. In the case of the deliveries, what you can get in the IP package or in the evaluation is kind of thing that what you get in the IP world anyway. So it's hardware development kit and the software development kit. In the case of the hardware development kit, it consists of the RTL inside the Verilog, system Verilog, or VHDL, some EDA scripts for integration purposes, some test benches, tests, and so on. So pretty much everything that you need for deploying the core into system on chip. On the SDK side, you have everything for the programming of the processor. So there is LLVM-based compiler, either C or C++. There are a set of libraries, either for C like NewLib or C++ libraries, low-level programming tools. There are quite a few simulators with different flavors and accuracy. There are also debuggers. Since we are LLVM house, we are using LLDB there for debugging, and OpenOCD as well. And then we also provide quite a few range of profilers, so then you can find the hotspots either in the software, or if you are doing customization, you can find the issues or some hints in the profiler as well, because the profiler can tell you which instructions should be added there, or help you with the selection of instructions that you would like to add into the architecture. These tools are usually the command line tools. If we would like to have a nice IDE, then we provide a code space. That's basically an IDE that improve the productivity of your teams, because you can do the debugging and profiling at the same time, inspect the results, and so on. So it's really nice tool that you can use. I was mentioning customization a while ago, so we're providing a solutions for customization as well. Speaking of customization, there are, like say, two basic approach, I would say, how you can do the customization. The first one is that you can do everything manually or in the standard way, I would say. That means that you need to patch the compiler, you need to add the support for low-level programming tools, debuggers, simulators. Then you need to verify a lot to check that everything's aligned and it actually has everything you need, and so on. There is nothing wrong in this approach, and you can still see that, but it's time-consuming, resource-consuming as well. So it's, it's general. It's quite challenging. So what if you can automate one or even the whole list that I was just mentioned? And this is exactly a reason why we created the Codasip Studio. So basically, it's a tool that allows you to do the customization in the most efficient way that you can have. The input to the studio is a processor description in the higher level description language. This is a C-based language that you can use, and basically you capture not only the architecture, so the ISA, but you can capture also the microarchitecture. So you can capture the pipeline, the units in the pipeline. So that's the input to the studio. Then you click on the button and you can get the whole set of deliveries that I was just describing a while ago. So you can get the compiler, you can get a debugger, simulators, virtual prototypes, RTL. Every single output that you get there is aware of the changes that you did. So for instance, if you add instructions, the C compiler is aware of these new instructions, and the compiler is able to use these instructions automatically. So there is no need to go to the inner assembly or intrinsics unless you want to. That's a huge benefit. Then you can use this for design from scratch, because the studio is designed in this way, or you can use it for customization of the processors that I just showed you. So every single one of them, every single processor that we provide is designed in this methodology. So then it allows you to do any modification that you can get or you can think of. But for this presentation, let's dive into the application class in more details and leave the customization on the side track. So in the case of the application class, right now it's available only in a 7 series. What that means is that there is a pipeline. There are 7 pipeline stages. It's mostly in older architecture. It's highly optimized for efficient compute with all the consequences it has. There is MMU, and obviously because we need to run RHOS, and it's SV39 at this moment. And the default ISA, actually there are 4 default ISAs that you can choose from. Either you have a soft float implementation, or you have a hard float implementation, and then you can enable the DSP extension or P extension. In the case of a float, we implemented high performance and efficient PU, and I will have dedicated slides on the P after that. If we dive into the application class RISC-V processors even in more details, then we can find out that it's highly configurable. So you can configure a cache. So you can configure how big it is, how many ways it has. You can configure also the branch predictor. So you can configure the BTB, BHT. You can configure these things. I was talking about the ISA already, so you can configure the ISA as well. In the case of a JTAG and RISC-V debug, you can configure either 4-wire or 2-wire implementation. And in the case of a debug, you can configure things like how many breakpoints you have, or whether you have program a buffer or not. So these are configuration options in the RISC-V debug as well. It's application class, so you can run either single processor or the multiprocessor versions of this core. I was mentioning the customization of this, so we already touched that. What I'd like to highlight here is that we provide virtual prototypes or simulators as well. So you can take the virtual prototypes and you can run them standalone, or you can integrate them into bigger SoCs. So then you can run or boot Linux quite efficiently on these simulators, because these simulators are high performance ones, including the cycle accurate one is quite fast, I must say. So then you can use these simulators for the virtual prototypes, for whatever virtual prototyping you need. The one feature that's inside of the application class is a P extension, which is a SIMD or packed SIMD extension. So you have a single instruction, multiple data approach there. And it's very useful for acceleration of the digital signal processing. So domains such as the audio encoding, decoding, computer vision, sensors, and even the AI or machine learning applications on the edge. So these are the domains that we can see or can leverage the DSP, but not only these domains, but just examples. So DSP can be used quite efficiently there. Unlike of the big vector extension, the P extension works on the integer register file only, so there is no additional register file. In the case of the ISA, it's quite complex because it has roughly about 350 instructions, but we split that into the groups, and you can enable or disable groups accordingly to your needs. So you can enable or disable certain parts of that. We implemented the most of the instructions as the single cycle instructions. The ones that need multiple cycles are fully pipelined, so then you have the high throughput in the case of a DSP application, which is quite desired in this case. So then the P itself is available in the application class, but also in the other classes like high performance embedded, as you saw in the one of the first slides when I showed you the metrics of the processors. The programming model is also important in the case of a P extension, and there are two main approaches or two basic approaches. One is, let's say, with the standard intrinsics or inline assembly approach, and that's available in the GCC. And there is also the second, more, let's say, friendly for software guys, and that's that you support the auto-vectorization or you support the C in general. And this is exactly what I'd like to announce right now, is that we do have LLVM C compiler that's able to do the auto-vectorization of the C that uses the P extension. So if you look at the right side, you can see an example of a C code. It's a simple foo function that takes two arrays and it does some addition. And if you look at the assembly that's below, it is produced by the LLVM compiler that we have. And as you can see, a compiler inferred proper instructions to do the SIMD operation. So the type of the A and B is a char, so you need to do ADD8 in this case. For this presentation, I just choose the simple constant for the size, which is 1024, but you can have functions that the size is just another argument, like the n, and you have a 4 up to n. And it's possible, and auto-vectorization works there as well. The thing is that the example is a little bit more complicated because you need to check the n value, and then it wouldn't fit slides nicely. So in this case, it's just for the slide purposes, but auto-vectorization works, or much more complex examples than just this one. So this is something that I wanted to share with you. The other thing that I wanted to share with you is that we opened a new design center in France, namely in Sophia Antipolis, so the high-tech place in France. We hired the experts in the case of the cache coherent design or protocols, as well as verification in this domain. So we hired veterans in the bleeding edge of the mobile computing applications and so on. So ex-ARM guys, as you can guess. So they are experts in not only in the design, but also on the verification methodologies and techniques that are used in the multiprocessor world. They started operating in the summer, so since then we have completed quite a few big list of tasks. So one of them we obviously completed the specification, and they already started writing the RTL and verification. So everything's on track because we have this branch to help design the multiprocessor solution for Codasip. If we look at the multiprocessor overview that we have here, you can see that we are targeting clusters up to 4 cores. The cache coherent L1, L2 will be configurable, and I have a slide on the configuration options in a minute. As the external interface, there's going to be AXI followed by CHI, so the system coherence will be supported as well. There is I/O coherency port as well. It's on AXI, similarly to the main external interface. Because the A70X, the application class, is highly optimized for efficient compute, this memory subsystem follows this pattern as well, so it's highly optimized for efficient compute. To verify and qualify this cluster, we are using real-life downstream IPs, so we are not just creating artificial verification environment, or we are using for verification and qualification real-life IPs to be sure that our cluster works as expected. There are quite a few features like prefetchers or power domains, as you can guess, to make efficient compute really at a good level. If you look at the configuration options that we have at the moment, is that, as you can guess, so we are targeting up to 4 cores. The L1 size is configurable. It's either 32 or 64K. The L1 goes up to 8 megabytes. You can also configure the number of ways the L1 or L2 has, so 4, 8, or 16. Cache line is configurable as well, so it's not fixed. It can be either 32 byte or 64 byte. You can enable the error detection or protection in L1 and L2, or you can disable that completely if you don't need that. It's similar to I/O coherency port, so you can enable that or disable that depending on your needs. I already touched the master interface or external interface, so it's AXI, and it's configurable as well in terms of the bit width, so it's either 64-bit or 128-bit. It's going to be followed by CHI later in the later stage. Speaking of the timelines, so the availability is as follows. So the evaluation packages are ready in Q1. The production versions will follow in Q2. And after that, the system coherence will follow as well. So as you can see, it's a quite robust solution if you are looking for a multiprocessor solution. So to conclude this presentation, as you saw, Codasip offers a rich set of RISC-V processors that targets different domains or different needs. So we have the low power domain, or class, if you will. We have the high performance embedded for DSP, and if you need a higher frequency there, and the application that's able to run rich operating systems such as Linux. We have quite a good members there. You can configure these cores as you want, or you can customize these cores as you want. In the case of the application core application class, you can run either single core version, or you can configure it into multi-core version, so depending on your needs. In any case, there is either floating point unit there, like the hard floats, or you can just have a soft float implementation, and the same goes with the P extension. So that's optional. So either you have it there, or you don't have to have there if you don't need it. We are huge believers in verification, so we verify every single thing inside of our designs to be sure that everything is in a good shape, the best quality that you can get. For the customization and configuration, we are using the EDA flow that's based on the architecture description language. So then we have the EDA tool that reads this architecture description language and produces the whole IP that you need for integration, including the RTL, including compiler that's aware of new instruction and is able to use this instruction automatically. Such as in the case of a P, where we can see that we have auto-vectorization for P in the LLVM. So you can really enjoy the programming models in C. Because of that, because of the studio, and if you need a customization, it's really beneficial because it saves you a time and resources in the case of the customization if you need it. Last but not least is that the IPs that we provide are really easy to integrate. So we offer everything you need. Be sure that you integrate the code correctly, properly, and everything is in place. Thank you for your attention. I hope that you enjoyed the talk, and I hope that we will see each other soon.